Thanks a lot, Jules. So good morning, everyone. Today I'm going to talk about building ETL pipelines with Apache Spark. And more specifically, I'll focus on two aspects of ETL in this talk. First of all, I'll start with talking about what exactly is an ETL pipeline and how is it different from a normal query execution pipeline. And then second, I'm going to talk about some of the existing and upcoming features in Apache Spark that are really useful for building these end-to-end ETL pipelines. So let me start off a brief introduction about me. I'm a software engineer at Databricks, where I focus on Spark Core and Spark SQL. I received my PhD in databases from UC Berkeley AMP Lab, where my research primarily focused on BlinkDB, which is an approximate query processing engine that was built in Spark. So here is an overview of this talk. As I mentioned, first of all, I'll start off my talk by talking about what exactly is an ETL pipeline. And in this context, we are going to talk about how this pipeline is different from a normal query execution pipeline. Second, we are going to see how we can leverage Spark SQL for doing ETL. And in this context, we'll be mostly focusing on two things. How does Spark SQL allow or help you to deal with dirty data? And in this context, dirty data might be data with just bad records or missing files, and so on and so forth. And second, we are going to talk about how can we build performant ETL pipelines using some of the state-of-art features around Apache Spark, more specifically Project Tungsten and whole state code generation. And finally, I'll conclude the talk by talking about some new features that are going to make their way in Apache Spark 2.2 and 2.3 that focus on building these ETL-friendly pipelines. So here, let me start this talk by a brief overview of what exactly is a data pipeline. So from a high level, a data pipeline is nothing but a sequence of transformations on data. Here, the source data is typically semi-structured, or it could be even unstructured. So examples might include JSON, CSV, or even a text blob that you're trying to process. The output data, on the other hand, is structured in some ways, and it's ready to be used by analysts and data scientists. And last but not the least, the source and the destination in these pipelines are often on different storage systems. So here's an example of a data pipeline. In this specific case, we have data that's basically coming from some logs or maybe a Kafka stream, and it's being ingested into a cloud warehouse. From this data might actually be fed into a database, which might then be accessed by a wide range of users. We can also have ad hoc queries directly on this cloud warehouse. Similarly, we can also pre-compute some aggregates, and these aggregates then can be served by some reporting applications in terms of metrics. And last but not the least, you can also train a machine learning model, serve it, and apply it back to the cloud warehouse. So this is just one such example of many, many data pipelines that we can build. Now, ETL is essentially the first step in building these data pipelines. It stands for extract, transform, and load. And the goal of the ETL process is to essentially clean and curate this data. It has three steps. First, we try to retrieve the data from the source, and this roughly maps to the extract phase. We then transform the data into a more consumable format, and this essentially is the transform phase. And we finally transmit this data to downstream consumers, and this is essentially the load phase in the ETL pipeline. So it is an example for an ETL query in Spark. So in this specific case, Spark is trying to read CSV data. So you can do something like spark.read.csv and give it a path that contains a list of CSV files. So this roughly maps to the extract phase in the ETL. You can then filter and aggregate this data in Spark, and this essentially is the transform phase. And finally, you can write this data to a file format like Parquet, which roughly maps the load phase in the ETL. Now, while this might look like just any other query in Spark, there are a number of reasons why queries like this actually deserve special attention. So let's see why queries like this, that the one that I just showed you, are really hard to implement and execute in practice. Now, there are a number of reasons why what makes ETL or queries like that hard. First of all, if we look at the source data, in that case, it was a bunch of CSV files. The source data generally is coming from a wide variety of sources, and they might be disparate. So the underlying data can actually be quite messy in practice. The source data might actually contain a lot of incomplete information, And to make matters worse, different sources of data might have different notions of how they represent incomplete information. So for example, maybe some data, if there's a missing field in some data, they might be represented as an empty string. Some other source might just tag that data as none. Yet another source might tag that data as missing, and so on and so forth. Now, since this data is coming from a wide variety of sources, this data can also be quite inconsistent across them. And basically, this means that data conversion and type validation in many cases is very, very error prone while building these pipelines. An example of this might be that you might be expecting an integer, but what you get is a string that wraps that integer. Another example is essentially you might be expecting a date in DDMMYY format, whereas what you get is a date in a different format. Yet another example might be things like CSV data, in which you might be expecting 5 fields, but the underlying data that you read actually does not have 5 fields. So all in all, the data can be pretty messy and inconsistent when you're trying to deal with these queries. Third, if you're dealing with streaming data or data that's constantly arriving, you are basically facing another whole new class of problems. So in this case, you suddenly have to care about at least once or exactly one semantics. You might also have to care about fault tolerance of the underlying system, and you might also have to care about scalability. How can the system scale up and scale down depending on the ingress rate of the data? And finally, to make matters really worse, the data itself that you're trying to read and extract can be quite complex in practice. So for example, it's not very uncommon to have deeply nested data, in case of JSON, that needs to be extracted and flattened out. And together with all the problems that we talked about, if you're dealing with complex data, all amounts of inconsistencies, all amounts of missing data makes these problems even more worse. Not surprisingly, the things that make ETL hard are exactly what makes ETL important as well. In a data pipeline, you want ETL to be the first step such that you can actually clean this data, remove all the messiness, so that the end consumers or the various consumers of this data pipeline now don't have to deal with this messiness and complexity. So on one hand, we see that executing queries, these ETL queries, is extremely hard. And on the other hand, if we look at many general purpose query execution engines, we see that this offer very little support for executing these ETL queries. So if you look at any general purpose query execution engine, it's designed in such a way that the moment you try to encounter a bad record or a corrupt data, it just fails the query. And essentially, these are not the same as transient errors. The next time you execute the job, it will encounter the same record, and it will just simply fail the query again. So all in all, there is no course of recovery in such cases. Second, a general purpose execution engine actually does not offer a lot of support around common ETL features. So things just like support for a wide variety of file formats. If you're trying to read different file formats, or you're trying to convert from one file format to another, have gaps in practice. Then you might actually lack a number of features that makes ETL queries useful, which is around multi-line JSON support, the date conversion things that we mentioned, and so on and so forth. And finally, since an arbitrary query processing engine knows very little about the data that you're trying to process, and the query or the extraction or the load phase or the transformation that you're trying to do on the data, it makes it very difficult to actually build performant end-to-end pipelines. So in the rest of my talk, I'll try to convince you that Spark's flexible APIs, support for a wide variety of data sources, and the state-of-the-art Tungsten execution engine makes it a great framework for building your end-to-end ETL pipelines. So let's see how we can leverage Spark SQL for building these ETL pipelines. So let's actually go back to the original query we had. You can actually write these ETL queries. A simple example of this can be as follows. Here, Spark is trying to read some CSV data, trying to do some filter or aggregates on the underlying data, and then it's trying to write it as Parquet. Now, when Spark basically sends this query to the driver then distributes this query to a wide variety of workers. Each worker in this case is responsible for reading one or more many files that's basically in this path. Now, one of the biggest reasons why queries like this actually fail in practice during the ETL phase is when many of these files might just be missing or can be corrupt. So in order to get around this problem, Spark actually allows you to explicitly ignore any such corrupt files by setting this flag spark.sql.files.ignore corrupt files to true. And if this flag is set to true, the Spark job should actually continue to run even when it encounters some corrupt or non-existent files. And the contents or the output of this job would still be returned with whatever files are valid and have been read, and it will just simply ignore the files that were corrupt. On a more fine-grained level, the other problem is in reading the ETL data, as we talked about, is when parts of the source data are missing or corrupt. So in this case, your entire file might actually be valid, but certain records might just be malformed or corrupt. So in order to get around this problem, Spark explicitly supports 3 different parse modes for parsing or reading JSON and CSV data. The permissive mode, as the name implies, tries its best to read as much data as possible and tries to basically get around the problem and informing the user in case it cannot read the data. The drop malform mode, on the other hand, can silently drop all the corrupt and malformed records from your query so that you just have to deal with the data that's normally better structured. And finally, the fail fast mode, as the name implies, fails the query as soon as it encounters a bad record, and the exception basically tells you which exact record is bad and what can you do about it. So let's look at each of these modes in context of JSON and CSV data as we go along. So in this example, I have a JSON file. It has 3 rows and 3 attributes, so A, B, and C. And as you can see, the first and the third rows are actually valid JSON, whereas the second row is malformed or corrupt. So now if we try to read this data using the permissive mode in Spark, it basically creates a table with not 3, but 4 columns. The 4th column, which is the corrupt record column, as you can see, essentially contains all the non-parsable columns or the records that have been queried. So in this specific case, Spark essentially would go on the second record. As it cannot parse it as a valid JSON file, it would just store it in the corrupt records column. And then it's up to the user to actually either fix the column, fix the row or the input data, or even filter it out depending on what the use case is by simply querying this table and corrupt record column just like any other table. By the way, you can also configure the name of this column using a simple Spark SQL flag, which is called spark.sql.column name of corrupt record. The drop malform mode, on the other hand, would essentially drop the second row from the output data. So in this case, you would just have an output with the first and the third row. And finally, if you execute or try to read this JSON record using the fail fast mode, we would actually just throw an exception. As shown, it would tell you what line it basically failed to parse on. So in this specific case, we tried to read the second line, and it basically failed to parse, and it will throw a malformed exception in Spark. So depending on the use case, we might actually use any of these parser modes to read and extract the ETL data. So I'll walk quickly through the CSV equivalent as well. So in this specific case, we have a CSV data, in which case we have 5 columns: year, make, value, model, comment, and blank. It has 3 rows. The first and the second row are somewhat valid, whereas the third row actually has only 3 values instead of 5. So in this case, if you try to read with the permissive mode would try to read as many rows as possible from this data. So in this case, it would automatically put nulls for the third row in the comment and the blank column. For the drop malform mode, it would just drop the last row. And finally, for the fail fast mode, it would just fail with an exception explaining which row it basically failed on. So in this case, it would just fail with an exception saying that it cannot parse the third row. So this was what Spark supports right now in dealing with dirty data and missing files and corrupt files. Now, in order to build performant end-to-end ETL pipelines, the other aspect of building these pipelines is actually to get or derive the maximum performance from them. So in order to actually build these pipelines in a performant way, the last few releases of Spark has been focusing on what we call as Project Tungsten, with the goal to substantially improve the memory and CPU efficiency of Spark's backend execution and try to push the performance closer to the limits of modern hardware. So if you look at the architecture diagram, Tungsten execution engine lies right at the bottom of the Spark stack. So any query that's written in SQL, Python, or streaming, any of the ETL queries would basically get converted into a data frame, which in turn gets executed over the Tungsten execution engine. So as part of the Tungsten project, we essentially had like a number of performance improvements as part of 2 phases. In the phase 1 of this project, which essentially encompassed around like Spark 1.5 and 1.6 releases, we laid the foundation of this project by working on better memory management algorithms. We also laid foundation to support this runtime code generation. And then we also implemented some cache-aware algorithms that could take advantage of these modern hardware properties. As part of phase 2, we really worked on 2 key things. First, whole state code generation, and second, vectorization that was able to basically make Spark performant by almost an order of magnitude for a number of operators. So I would actually not go too much into the details of Spark's performance and essentially the whole execution engine, but I'll be talking about this in a talk later today at the end of the day, actually, when I'll be talking about Spark SQL and how it actually compiles queries from like just SQL queries to RDDs. And this talk would be at 5:40 p.m. And in that talk, I'll talk about Catalyst and the Tungsten execution engine in much more technical detail. But let me give a brief overview of what these performance related work actually gave us in Spark. So here what I have is some kind of operator benchmarks, or the cost per row, or cost of processing each row in each of these operators in nanoseconds. And the primitives I have is various operators in Spark that are pretty common in ETL. So you have filters, aggregates, joins, maybe sorts, and things like that. And this compares 2 things. It compares Spark 1.6, which is an older release of Spark, to Spark 2.0, which is a considerably newer release of Spark, and contains all our improvements around whole state code generation and vectorization. So as you can see from the slides, for a lot of these operators, filters, aggregates, hash joins, we were able to almost obtain around 5 to 30 times speedups between Spark 1.6 and 2.0. For things like sort, we were able to implement radix sort algorithms that gave us around 10 to 100 times speedups between these 2 versions of Spark. For things like sort merge join, shuffle still remains the bottleneck, and we'll continue to work on mitigating this bottleneck. But for now, we don't see a massive speedup in these cases. And finally, for things like Parquet decoding, or essentially trying to read Parquet data, we were able to again get speedups of about 10 times because of a custom vectorized reader Parquet vectorized reader implementation in Spark. So the high-level takeaway from these slides is essentially that due to the ongoing work in Spark and the whole efforts around the Tungsten execution engine, it makes it a really optimal execution framework to build your ETL pipelines. And again, like this is just one slide that talks about a real-world benchmark. In this case, it's a TP-CDS benchmark with a scale factor of 1,500 and 100 cores. And this again talks about how Spark 2.0 is roughly 2 to 3 times faster than Spark 1.6 and previous releases. So the x-axis here is the like number of TP-CDS queries that we can execute in Spark 1.6. And the y-axis here is the query time. So each pair in this graph actually represents a query execution in 1.6 and 2.0. And as you can see, the blue bars, which are Spark 2.0 times, are considerably lower as compared to 1.6. So we have not only worked on improving the per operator cost, but these, as you can see, translate very well into like full-fledged queries, which include these ETL pipelines. So next, as Matej talked about in his keynote yesterday, let's try to see what are some of the upcoming features in Spark SQL, especially in 2.2 and 2.3 releases, that focus on building these ETL-friendly pipelines. So let me try to give a sneak preview of a number of features that I'm most excited about when we build these pipelines. So from a high level, these features can actually be divided into 3 categories. First, we would like to provide some better functionality while you want to build these pipelines. So in this case, things might include better JSON and CSV support when you're trying to read this data. Second, there is a whole lot of work being done around usability. And this includes tweaking a large number of exception traces such that you can generate better error messages to the user so that you can exactly know which column or which record is actually faulty, and then we can do something about it. And finally, we are always focusing on better performance. So in this case, we are focusing on a better more performant SQL execution engine. And we are also working on better support for Python UDF processing. So I'll spend like a little bit time on each of these 3 bullet points as we go along. So in terms of functionality, Spark currently can only read JSON data 1 line at a time. And this means that every time you want to read some kind of multi-line JSON, it requires custom ETL. But as part of Spark 2.2, we are working on this Spark 18352, which includes native multi-line JSON support in Spark. And in this case, you would just be able to point Spark to any JSON path and just use this whole file option and set it to true. Next, we are also investing a lot of time and energy in supporting higher order functions in Spark SQL for manipulating deeply nested data. And in this case, you can have operations like map, filter, reduce on complex data types. You can think of arrays and maps that can just be manipulated in SQL or data frames. So as an example, consider a table in which you have a key that's a long type and values, which is an array of longs. So in this case, if you want to actually manipulate this data, in this case, let's say, hypothetically, I would like to append the key to the list of values. It's really complex to write these queries such that you can actually write them in a more performant fashion. In Spark 2.3 and beyond, once we add these higher order functions in SQL, we would be able to essentially write transformations or map functions like this. So in this specific case, if I'm trying to basically append this value of key to the list of values, we can just essentially do something like select key transform, which is essentially a map function, which takes in these values or the second column in this table, and then it maps these values and appends this key element to these values. So as I mentioned, these operations might actually include these transformations or filters or reduce operations and things like that. Next, we are also working on a much more improved and performant CSV data source. And improvements in this class of line actually might include multi-line CSV support. It can include a wide range of options for additional CSV parsing. And finally, a whole text reader for data frames. And again, this would be released in Spark 2.2, which would be code freeze later this month. And finally, we are always working on better, from a functionality standpoint, there is always a need for better ETL support. And this is actually a wide range of JIRAs and PRs that are basically going into this effort. And the goal here is to actually have more fine-grained tolerance or record-level tolerance to errors. So we saw some examples of it with these new parser mode, but we are trying to extend it further in order to provide users with the control on how to handle these errors. So as we already saw with the corrupt column, you could actually ignore and report these errors post hoc in some way. You scan your data, you basically put all the non-parsable records in that column, and then you can report these errors back to the user. But we can also add some more support. For example, in this case, we are thinking of adding a support to ignore bad rows up to a certain number or percentage when you're trying to read this data. So this, again, would be available in Spark 2.2. And finally, from a usability perspective, as I mentioned before, we are continuously tweaking a large number of exception traces to generate better error messages. And the key idea behind this effort is to make sure that Spark can not just throw an exception to you in case something goes wrong, but also try to explain why the underlying data is bad. And this is especially true for data conversions, where many of you, when you try to read some data, might actually see some exceptions like this, a match error when your data type does not actually match the schema type. And this exception itself is actually pretty useless because it does not really tell you which row or which column of your data is actually failing and how this exception actually maps to your underlying data. So as part of this, and again, this is an ongoing effort because there are a lot of exception call traces that needs to be tweaked. We are trying to essentially augment these exceptions with better failure messages around what rows and what columns can actually be at fault. And finally, if we talk about performance, two major things that I'm excited about. The SQL execution engine in itself has three really exciting initiatives that are going to make its way in Spark 2.2 and 2.3. First of all, as you might have heard the talk yesterday, Spark 16026 adds support for a cost-based optimizer in Catalyst, which essentially will be able to leverage table and column level statistics to optimize joins and aggregates. Examples might include just basically picking the right join type or join reordering and things like that by figuring out the cardinality of many of these operators. And as part of this, in Spark 2.1, the community has already integrated the statistics collection framework. And then there has been efforts and considerable efforts in the direction of integrating the cost-based optimizer in Spark 2.2. Second, we have also been working on boosting Spark's performance on many core machines, or on single node machines. And as part of it, we are working on an in-memory single node shuffle. And last but not the least, there is also a massive efforts in improving the quality of the generated code, so in Spark. And this includes better integration with in-memory column formats in Spark. So all in all, a wide variety of improvements around the SQL execution engine are going to make its way in Spark 2.2 and 2.3. And finally, Python UDFs. Python, as you know, is the most popular language around doing ETLs. And in a way, Python UDFs are often used to express these elaborate data conversions and transformations in your ETL pipelines, which means that any improvements to Python UDF processing will ultimately improve ETL. And as part of this, in Spark 2.2, 2.0 and 2.1, we have been actually working on adding a lot of support around Python UDF chaining, spilling, and things like that. But I'm actually not going to talk a lot about it, because the next talk in this session would focus precisely on that. In fact, Wes would probably talk about how you can improve Python and Spark's performance and interoperability, and talk a lot about like these Python UDFs and performance implications around it. So just a recap of my talk. In this talk, I focused mostly on three things. First, we talked about what exactly is an ETL pipeline and how is it different from a regular query execution pipeline. Unlike a regular query execution pipeline, which is basically designed to finish from the start to end, an ETL pipeline essentially is designed to work well with exceptions or corrupted data. So in that case, it's very different in terms of an execution engine when you try to execute that pipeline. Then we talked about how Spark SQL can actually be leveraged to build these ETL pipelines. And in this context, we talked about two things: the support for Spark SQL in dealing with dirty data, such as missing files and bad records. And then we talked about how Spark SQL 2.0 and beyond are actually devoting massive efforts around this project Tungsten, which is essentially helping us build the next generation performant execution engine. And finally, we kind of like did a sneak preview of many upcoming features in Spark 2.2 and 2.3 that focus on building these end-to-end ETL-friendly pipelines. With that, I'll conclude my talk, and I'll be very happy to take any questions.
Thank you, Samir, for that wonderful, insightful thing about how to get rid of all the ETL exceptions. Do we have any questions? We have two mics on either side of the row. Can you please proceed to the mic and ask your question? We have about a couple of minutes, so let's keep the question short.
Great talk. I would like you to elaborate more on the boosting performances on a single node machine.
Sure. So there are like a bunch of bottlenecks around like single nodes. One of the things that essentially is like the bottleneck that we identified in the short term was if you're trying to do like single node shuffles. So this was actually the slide that I was talking about. And normally, like if you're trying to do this shuffle across a single node, we saw that the in-memory access between these shuffles quickly became a bottleneck. So in this specific case, we are trying to actually work in designing like the shuffle operator that can work well with single nodes. And in order to know more about the technical details of what is being done, I would actually refer to Shifan Pu's talk like in Spark Summit Europe last year. Shifan worked with us at Databricks last summer, in which he actually worked in optimizing these like shuffle-based operators. So all in all, I mean, there is a number of efforts that are going around like these shuffle. The other thing that's going around is like we are also exploring some data structures that can actually be multi-threaded, and they can actually take advantage of these multi-core processors in a much more performant way. But this is still like something that is being done.
Anybody else? Yeah, go ahead.
Hey, this is a great talk. So I have a quick question. Like in our ETL pipeline, what is happening is we have a lot of data sources where we pull data from REST APIs, FTPs, and other places. So right now what we are doing is we pull all the data using a single threaded application, and then we read it as a Spark text file or a data frame. So is there anything in future like where we are coming up with the operators where we can directly talk to REST APIs or FTP or SOAP up files?
So the question is like if Spark actually can have like support for directly talking to or pulling data from FTP. I think there are like some third-party connectors in Spark that can actually pull this data, but I am not like completely aware of like, I mean, what's the state of art there right now. But I mean, essentially there are definitely connectors that can actually pull this data from like these third-party data sources.
Okay, thank you.
Go ahead.
Hello, great talk. Have you ever thought of using fine-grained validation on specific attributes? I know it's a bit difficult to use it on data frames, but what about RDDs or
Can you give me an
datasets?
example of what you mean by fine-grained validation? Like, is it the type of the attribute or?
For example, let's say that I have a CSV with the attributes, and I want the first attribute to be a string, the second numeric, and the third date, something like that.
Yeah. So basically, in many of these cases, you can actually provide a schema that you would want to parse this data as. And in that case, I mean, Spark would automatically validate and try to throw an error in case that schema does not match. Unfortunately, the state of art for such errors is actually not very good. So the Scala match error that I talked about like, is one such exception that Spark will throw if your attribute type does not actually match with the underlying data type. So as part of the usability effort, we are trying to improve error messages like this. And in this case, like Spark would be able to tell you exactly which record and which column is actually at fault.
I'm afraid we're out of time, so please give a big hand to Samir for his wonderful talk. Thank you.